So next topic, actually it's actually has come very close to the note point, so I'll just move the next topic a little down, so it will not be disturbing this topic. I've moved the next definition side heading down, little down. So this is the note point, so I'm ending the note point also here so that it will be clear. So just some extra lines I'm removing. So this is about the the particular derivation. So therefore we are getting the final equation. This is the completion of the derivation. So now how to write the running notes. So there's not much derivation, only one step, main step. By definition of electric field intensity, E is equal to force on unit per charge. This directly from Coulomb's inverse we are getting. In the next step itself, we are getting the answer for electric field intensity. E is equal to 1 by 4 pi naught q by r square. So what are the two lines? Only 2 or 3 lines should be written in explanation. So it's like this. So A is a point, capital A is a point, A is a point at distance small r from isolated charge q. Next, by definition of, so when a unit positive charge plus 1 is placed at a next, so when a unit positive charge, unit positive charge means simply plus 1, it's shown as plus 1 in the diagram. So unit positive charge, this is a regular symbol for unit positive charge, plus 1 units. Actually units, it's difficult to write, it diagram becomes ugly, congested if another word units is written, also written. So plus 1 is much more simpler. When a unit positive charge is placed at A, it experiences a force F. By next sentence is by definition of electric field intensity. So see here, explanation is taking a little time, but still doesn't matter. So it is directly based on definition, not difficult to write, not difficult to understand also, very simple. By definition of electric field intensity. So this sentence and this sentence appear to mix. So this is different. I'm just drawing a separating line. So here this is a different sentence. Just see, it experiences a force F. After that, by definition of electric field intensity, E is equal to F on unit positive charge, F on plus 1 charge. So after that, remaining steps are same, no complication. So this is how the running notes can be completed. Very simple. So running notes should not be taken lightly because this is a derivation. Derivations are again as powerful as scientific definitions and the laws or the principles of that lesson, or the fundamental laws, or at least the laws of that particular lesson, because each and every step of a derivation is based on a definition or a law. You see here only two steps are visible. First step is definition, second step is Coulomb's inverse square law. So derivation is a very powerful application of the scientific definitions and the fundamental laws. That's why it's so important. They should not be taken lightly. Don't think that only two steps, regular steps, it will not be useful for solving tough problems. Tough problems are nothing compared to scientific derivation. Tough problems can be given or solved by anyone, but scientific derivations were given by only few scientists. Anybody cannot give scientific derivations. Only few of them. If anybody can give a scientific derivation, he'll also become a scientist. Only few scientists we had till now. In future also only few scientists will be there. But always a student should be aiming to become a a very good scientist or a very good engineer. A very good scientist always will be partly an engineer, and a very good engineer will be partly a scientist. Then only they can be very good scientist or a very good engineer. Always students should be aiming to become one, or anybody related to science and technology, they should be aiming to become always the best in the field. That means the best scientist or the best engineer. So this is the simple derivation. So next topic, simple topic, electric line of force. So what is an electric line of force? Now this topic already you have learnt to some extent in the previous years. Here again it is very important because it's a definition that makes it even more important. So what is an electric line of force? Now consider a simple situation. So here actually little space is there. So actually it's not sufficient. So I'll just move the next slide heading a little more down. So this next slide heading is actually properties of lines of force. So this side heading I'll just move it a little more down, so it will not be disturbing the this definition. So what is electric line of force? Now consider a, an isolated positive charge again. So this is an isolated positive charge. Near this isolated positive charge, around this isolated positive charge, electric field is present. Now electric lines of force or electric line of force is a special line, or electric lines of force are special lines using which electric field can be very easily understood. Just by looking at the electric lines of force and electric field, the nature of the electric field can be clearly known. What is the direction of the electric field? Direction of the electric field is nothing but direction of the electric field vector. So very clearly looking at the lines of force, in what direction electric field is acting can be clearly known. Where the electric field is more stronger, where the electric field is less stronger, that also can be known. But from this equation, based on from this result which we got from the, so this result is also again another powerful result. So it's called as, say, result 1. There is only one equation obtained in the derivation. So it's simply shown as result 1, separate special result 1. So now it can be seen that far away from the charge q, at that means more distance, electric field is very less strong. The strength of the electric field is very less. Close to the charge q, supposing the charge q, we're taking a point very close to the charge q, R is very less. That means strength of the electric field is very high. From the equation, we are able to understand the strength of the electric field. Not only from the equation, even with the help of these special lines of force called as electric lines of force, drawn an electric field, we can easily understand where electric field is strong, where electric field is weak. The magnitude of the electric field we can easily guess, or we can easily understand. Not just the magnitude, even direction of the electric field also can be known with the help of the electric lines of force. Not only this, they have even more uses, electric lines of force. So powerful are they. Very powerful laws in electricity are actually given in terms of these electric lines of force. Very powerful laws. They are so powerful that many complicated problems they can just solve in one step. All such laws are actually given with the help of these electric lines of force. They are actually imaginary lines. They don't really exist. But still, they are very helpful in understanding many things in electricity, both static electricity and also different branches of electricity. Now consider an isolated positive charge. Now near this isolated positive charge, at any point, say at this point, you put a tiny positive test charge. A tiny positive test charge, tiny positive charge, say like this. It's a tiny charge. It's difficult to draw smaller than this actually. So I'll try to draw it using a sharp pen. So a tiny positive charge is placed here. Important thing is it's a positive charge. So immediately this positive charge will repel it. So the direction of the repulsive force will be away. So exactly along the line joining the centers of the two charges. Imagining that both the charges are point charges. So it experiences a repulsive force. So in that direction it will be pushed. So it will go along this direction. So exactly straight line path it starts taking. The more it goes, still everywhere field will be there. So further it will be pushed. So continuously what is happening is this positive charge, tiny positive charge, it's called as test charge. Test charge means It's a charge which is used for testing the field. Now this tiny test charge immediately experiences a repulsive force and it goes along a straight line. So this straight line will be going like this. So this happens wherever the tiny positive test charge is placed. So even if it's placed very close to the given isolated charge, also the same thing will be happening. So it will be taking this particular path along this direction. Similarly, at any other position, you put it here again, it will be getting repelled and it goes along this path. Now such lines along which a free positive charge moves in electric field when the free positive charge is placed at any point near the in the electric field. Such lines are simply called as electric lines of force. They are called as imaginary. They are simply called as imaginary. Now, why they are called as imaginary? Now, the reason for this is this tiny positive charge which is actually placed here. What happens is it will be disturbing this charge which is already present here. So it is imagined that, so how it will be disturbing? The reason for this is whenever a charge is brought near a body, there is a phenomenon called as electrostatic induction. There is a simple phenomenon called as electrostatic induction. So what is electrostatic induction means? Even if an uncharged body is brought near a charged body, for example, near this charged body an uncharged body is brought, what happens is on both sides of the uncharged body, charges are actually formed. So that's what happens if a test charge is brought near it. So immediately this charge will be actually getting disturbed. Once the charge gets disturbed here on both sides, on one side charge will increase, on the other side charge will decrease if it's already charged. If it is uncharged, charges will be actually getting formed. So due to this reason, once this charge is getting disturbed, electric field also gets disturbed. So it is not possible to bring a test charge here without disturbing the existing electric field. That's why the lines of force are said to be imaginary. So if a test charge is so small, tending to 0, then this will not be getting disturbed. This charge will not be getting disturbed. So we'll be getting the electric field will be existing as it was earlier. So but still this is an imaginary situation because as charge tending to 0 is very difficult to get something imaginary. So lines of force are also imaginary. Now another very important thing is this test charge that is brought here. It is called as a free charge. Free charge means this should be experiencing a force only by this charge, or that is only due to this electric field. No other force should act. That means like gravitational force or any other force should be absent completely. Such a test charge is called as free test charge. So such a free positive test charge, when it's placed at a point, the line along which, or the imaginary line along which it moves, is simply called as electric line of force. So that's a simple definition. So it can be seen that the directions of the lines of force near the positive charge are directed away. So the lines of force are said to be diverging from each other. That means as they go more and more distance, the lines of force, they are more and more getting separated. They are said to be diverging. So always the lines of force near a positive charge, they will be diverging away from the positive charge. Then what about a negative charge? So it is easy to guess. So negative charge, the lines of force will be like this. So this is a negative charge. Supposing you are putting a positive test charge here. Always everything in electricity is defined using positive charges. See here, we have seen the definition of electric field intensity. How it is defined? It's defined as a force on unit positive charge. It's not defined as force on unit negative charge. Because standard positive charge is taken as a standard charge. Every definition that is used. Because once what is the direction of force on positive charge is understood, automatically negative charge force will be opposite. So it will not be difficult to understand. So for that reason, everything for the sake of uniformity, everything in electricity is defined using positive charges. That is using a positive test charge, whether it's a positive unit test charge, whether the test charge is a unit positive charge or the test charge is a tiny positive charge. But the electric field can be due to a positive charge or the electric field can be due to a negative charge. So that doesn't matter. But definitions are given only using positive charges. Force on unit positive charge. The line taken by the line along which a free positive charge is placed at a point in electric field moves. That is called as electric line of force. See the definition. That line along which the free positive charge moves itself is called as electric line of force. The direction in which it moves is called as the direction of the electric line of force. That way. So now we are considering electric field produced by negative charge. Now again here, what is the electric line of force? Again we are putting a positive test charge here. So when you are putting a positive charge, immediately it will get attracted. So it takes a straight line path towards the negative charge. So the direction of the line of force here will be what? Towards the negative charge. Similarly, if it's placed here, again it will get attracted. So the lines of force, clearly it can be seen that near a negative charge or an electric field due to negative charge, the lines of force will be towards the negative charge. So always the lines of force near negative charge, they will be converging at the negative charge. Whereas near the positive charge, they will be diverging away from the negative charge at the negative charge. So near a positive charge, the lines of force due to a positive charge will be diverging away from the positive charge, and due to negative charge, the lines of force will be converging at the negative charge. So these are the two very simple properties of the electric lines of force. But the main thing is what is an electric line of force? It's said to be imaginary. So how will be the definition? It's an imaginary line or curve along which a free positive charge moves when the free positive charge is placed at a point in electric field. That's a simple definition. And what are the examples of lines of force? These are the two simplest examples of lines of force. So definition of lines of force, you see. Now here we can see that lines of force are imaginary lines. Definitely it can be seen that in both the situations lines of force are actually straight lines, and they can be curved also. Really they can be curved. Both the cases electric fields are actually fields due to isolated charges. What if I combined a pair of positive and negative charges is taken? Then how will be the lines of force in such a situation? So this is example 1 we have taken. This is a separate example. This is another example, separate example. Now we'll take a third example. What is the third example? Where field is due to both the charges. This is separated. This is isolated positive charge, this is isolated negative charge. Both are separate examples. What if we take a pair of charges, equal and opposite charges? Equal and opposite charges is also called as dipole. Then how will be the electric field due to such a dipole? That is a pair of charges. That in that case it can be curved also. So how to understand this? This can be understood like this. Actually there is no place here. So I'll do one thing. So properties of electric lines of force. I'll just shift it to another page. So the side heading I'll just shift it to another page so that this space will be there for the diagram. So this is the next page, new page actually. So this is the new page. Now we'll come back to the regular page. So now consider the third example. So in the third example of lines of force, consider the pair of equal and opposite charges, positive and negative charges. Now if you are putting exactly, consider the line joining the positive and negative charges. So here you are putting a unit positive charge here at this point. Immediately it will be repelled by the positive charge, it will be attracted. So it will be moving away from the positive charge towards the negative. It goes exactly along the straight line path. Similarly, exactly along the line joining. So this is the line joining the two charges. On the left side of the positive charge, if you are putting the unit positive charge, it will be pushed away from the positive charge. So it takes leftwards direction. Exactly along the straight line path it starts moving, but at the same time it will be attracted. But attractive force will be negligible because the reason is negative charge is far away. So positive charge force will be dominant. So resultant force will be only repulsive force because attractive force will be cancelled by the repulsive force due to the positive charge, and because it's greater, the resultant force will be in the direction of the greater repulsive force, so it will take leftward direction. So exactly line of force will be directed away from the positive charge again. So here also we can see that direction of the lines of force is away from the positive charge and towards the negative charge, as we have seen in the two separate examples 1 and 2. Now again you consider the line joining the two charges but on the right side of the negative charge. Here we are putting the unit positive charge, then what happens is it will be attracted by the negative charge but at the same time repelled, but attractive force is greater, so it will be really moving towards the negative charge. So line of force will be directed towards the negative charge. So this is okay along the line joining the positive and negative point charges. Again taking here also point charges, This is also called as dipole, and this is called as axis of the dipole. So axis of the dipole, definitely lines of force are straight only. But if you take any other point, supposing here you are putting the unit force charge, then as it gets repelled, as it goes like this, at the same time it's attracted by the negative charge. So it will take a curved path, the unit force charge, and go towards the negative charge. So here it can be seen that really it is curved. Similarly here below also, this way. Similarly here. So it will go like this and it will come here. So the lines of force are starting at the positive charge and ending at the negative charge. Here there is no place. So it will go like this, it will go like this. So another line of force, it will go like this. It takes a big curve and comes back here. So diagram of the, okay, here just, so it will take a big curve and again it will be ending at the negative charge. So here again just see, it gets repelled by the positive charge, but because of attraction at the negative charge, it will slightly turn towards the negative charge. It takes a big curve and again it will be ending at the negative charge. So here also the same thing can be seen. The lines of force are diverging away from the positive charge and converging at the negative. So we are getting a crab-like diagram. This you have seen many times in the school also, this diagram. So the main thing is all these things are directly based on the definition of the electric line of force. So the most powerful thing here also we can see that it's nothing but the definition itself. So definitions should never be taken. Each and every property can be understood clearly related to the lines of force. So lines of force definition carries just 1 mark in the board exam, but still it should not be taken lightly. So actually there is not much place here to write the marks also. So it doesn't matter. It can be written as clearly as possible. So this is 1 mark topic. So just definition. But still, because it's a scientific definition, it should be by hearted. Any complicated problem can be solved with the help of this scientific definition. So it is, each and every word is important here. It is an imagine, it's real, it's not real, you see, because this is an imaginary situation. Test charge, it's actually not possible to have without changing the field, existing field. So it's just imaginary. It's an imaginary. Each and every word of a scientific definition are important because they were given by scientists by careful, very accurate thinking. So it can, nobody found out any mistake in that later. It's an imaginary line or curve along which a free positive, so I'm writing positive in short. So actually in the board exam you have to be careful, you have to write your grammar also properly. That will not be required in entrance examination. Entrance exam, how fast you are solving the problems, that only is important. Both are actually useless. Grammar is less important. Grammar is actually again like laws in languages, but here the laws in science and technology are the fundamental laws or the laws of that particular lesson. Only they are important here. And in entrance examination also it's something useless. So this entrance examination only quick solving of the problems is seen. Depth of the subject, such questions cannot be set by the faculty. The reason is they take a lot of time. So much time. It's not, earlier they used to give essay questions, but the faculty used to get killed by those essay questions. Half mark more, half mark less. It becomes very difficult. So everything is made computerized now. Question paper correction is done by computers. Only numericals. So that's much more. That has become much more simple. So no depth of subject is required. Just the intelligence of a student, not the devotion of a student, can't be tested. So the student who takes very good marks in physics, actually he'll be taking computer languages. So he goes to languages side finally. And after taking computer languages, it's called computer science. It's only namesake science, entirely deals with computer languages. There's no science in that. And after completing computer sciences, the student will be either going to computer science or he'll be taking going to business. So there's no, whatever he studies throughout the life, he'll be forgetting and going to something else. Some other job he'll be doing. So there's not much use, but few students will be going in the selected chosen science field of science really. So but that doesn't matter. So whatever So whatever is actually presently convenient, so it doesn't matter. So whatever is convenient for the student, it can be done. So I'm just giving an example. So I'm just giving this example not to disappoint the rank scorers. Those who are interested in subject, I'm just pointing out the mistake. So I want to convey clearly that those who are interested in the subject, you need not be disappointed. You can take your own time in thinking about the scientific derivations and can spend more time on derivations and less time on problems if you wish so. But you have to be careful that you get sufficient marks. If you're thinking too deeply in the scientific derivations or scientific topics, marks will get reduced. The reason is you'll be covering less topics. Time will not be there for covering many topics. You'll get, if you're getting less marks, so you can't get a free seat. So education will become costly. So you have to be moderate. So some time you have to spend for deep scientific thinking, definitely, but more time you should be spending time in solving problems and solving the problems quickly, whether you like it or not. Okay, so coming back to the lesson, it's an imaginary line or curve along which a free positive charge moves when placed at a point in an electric field. That's all. This is a very simple definition, and below the definition, we have three examples of the electric lines of force. No explanation for the examples. So from these examples only, all the properties of electric lines of force can be obtained. They are very, very, very useful properties because many derivations are based on these simple properties. About 6 or 7 properties are there. So this is the completion of this particular page.